We have two talks in the next session before afternoon tea, and the first talk is by Amy Wilson. We're going to talk about accounting for uncertainty using computer models as decision support tools in energy systems. Okay.
So thanks for the introduction. Is this working? Yeah. And thank you very much for inviting me to speak. As you say, my talk's going to be on modelling uncertainty when using computer models as decision support tools. And kind of the overarching message of my talk is that when you're using computer models to make policy decisions, it's really important that you have a sort of logical framework to model the uncertainty, to link the computer model output to the real world decision that's being made. And I'm going to talk about some sort of statistical methodology that you can use to do that. So I'll start off by talking a bit about the sort of very generic methodology which can be used in all fields, and then I've got two examples in energy policy. So I'm not sure I need to have this slide since we've been talking about models all week, but just to include sort of some notation, what do I define a computer model? It's some approximation of a system or a part of a system. It takes some inputs, you crunch some equations, and you get some outputs. Okay, so my inputs would be this x, my computer model is the f of x, the function, and y is my outputs. And if we're using a computer model to look at a decision problem, we might split x into two, theta and z, where theta would be the control variables of the decision variables, and z would be some uncertain parameters, like that doesn't have anything to do with your decision, like say demand forecast or something like that. So this is the second time we've had this slide this week. I think Jalal had it the other day. So George Box said essentially all models are wrong but some are useful, and so I'm saying if you're using a computer model to take decisions in policy, we all know the model's wrong, so how do we go about quantifying how useful it is? And I would say you do that by studying the uncertainty in the modelling output and how the modelling results that you have link to the real world decision that you're trying to make. Okay, so there's sort of, as we all know, lots and lots of different types of uncertainty. The sort of main one that people tend to think of is parametric uncertainty. That's uncertainty about the appropriate input parameters to use, Z. So for example, if you're plugging a demand forecast into your model, that's going to be uncertain. Then another one which people think about a bit less is structural discrepancy. So this looks at how does the model, the function f, relate to the real world process it's modelling. Okay, we know the model is an approximation, so how good an approximation is it? For example, you might say something's normally distributed, or use some smoothing parameters or something in your model. So what effect do those simplifications have in terms of the difference between the model and the real world? And then the last one, which is what most of my talk's going to be about actually, is function uncertainty, which looks at what is the output of the model f of x at x that you haven't tested. Okay, so this is saying normally in big modelling studies we run a number of scenarios, so we have x and f of x at a small number of discrete points. Outside of the x's that we've tested, we don't actually know what f of x is, and that can sometimes make looking at uncertainty challenging. So I'm going to be talking a lot about methods for modelling this function uncertainty, and then once you've done that, how can you use that to model particularly parametric uncertainty? But you can use the same types of things for structural discrepancy as well. Okay, so a typical method in industry or government, say, would be to get a small number of deterministic scenarios for the uncertain parameters z, run them through your model, and try and find the control parameters theta that give you some maximum or minimum, say, under each of the scenarios. And I think we all know that this is a bit problematic because it gives us a limited exploration of the uncertainty because we're only testing it at a number of small points. And often Z has high dimensions, so it's sort of a very small proportion of the overall input space that we're looking at. And also this doesn't tend to look at correlation between different inputs. So this is sort of a method for looking at parametric uncertainty, which is often used. It's becoming more common in industry and government, I think, to use Monte Carlo simulation where you put a distribution over your unknown input parameters z, and run it lots of times after drawing from your distribution and get a distribution over the output, and then that's sort of modeling your parametric uncertainty. But this doesn't work if you have a model that's too slow to use for Monte Carlo simulation, because you'll never be able to take enough draws from your input parameters to get a good idea of the uncertainty in your output. Okay, and that's where this function uncertainty comes in, because now we can't do parametric uncertainty because we have no idea of what the function uncertainty is, because we can't do enough runs to get the parametric uncertainty. Okay, so what can we do about that? So one method, which is again for these large and slow models, is to build something called an emulator. So an emulator is a statistical model of an underlying computer model, basically. So it's kind of similar to things like response surface, meta model, approximate model, but the idea of an emulator is it's not just approximating the output, it's actually a distribution over the output. Okay, so it's encapsulating the uncertainty of your output given a particular input parameter. So for example, if you wanted to do look at parametric uncertainty, you take a draw from your distribution over your input z, and then you can use your emulator to give you a distribution of the joint distribution of the output of the computer model over all of those inputs. That kind of makes sense. So the emulator is effectively modeling the function uncertainty, and then you can combine the emulator with a distribution over your inputs to look at parametric uncertainty. Okay, so methods for doing this are fairly well established in academia, but these methods aren't widely used for taking policy decisions in practice, with the one exception of climate change, where they are used. So David can tell us more about that. Okay, so here's some graphs to try and illustrate the point a bit further. So say I have a computer model, the input's my x-axis, the output's my y-axis, and I run it at 5 points. Those 5 dots would be the 5 points that I've run it at. So at those 5 points I know exactly what my input is and I know exactly what my output is. Okay, so I would want to fit an emulator to these 5 points, so the data that I'm fitting to is the model runs. And if I was thinking about what my model output could be at places other than those 5 points, well, it could be functions which pass through all those 5 points. Okay, so an emulator is effectively a distribution over those functions. So for example, something like this, the blue line would be the mean of my emulator, and the red line would be 2 standard deviations of that statistical model. So the uncertainty is going to 0 at the points that I've run, and the uncertainty is getting bigger the further I get away from points that I've run. Okay, so that's encapsulating my function uncertainty, basically. So how could I use this to look at parametric uncertainty? Let's say I have some uncertainty in my demand. I can pull that across to look at how much that is giving me uncertainty on my y-axis. And the important thing here is that I'm not just using the blue line, so I'm not just pulling up demand and then pulling it across. The final uncertainty in my cost is a combination of the parametric uncertainty in my demand and the uncertainty that's coming from my emulator. So that is both the parametric uncertainty and the function uncertainty. So I've got the both together. Okay, so that's why it's kind of better than using an approximate model or response surface. Right, and let's say I had that and then I wanted to reduce my function uncertainty. Well, I could go away and run another point there, which is going to make it smaller. That will reduce the uncertainty in the y-axis or the cost by running another point and getting better uncertainty bounds on my emulator. Okay, so that's the sort of general idea of emulation. So how should we go about setting up these emulators? A standard approach is to use something that looks like that equation there. So you would say the output of the computer model f of x is equal to some coefficients times some basis functions, so similar to a regression line, plus some stochastic process epsilon of x. And the stochastic process is sort of standard. Often a Gaussian process is used, and you set a prior covariance for epsilon of x, and then you have parameters would be your beta, one for each basis function, and you'd have parameters in the covariance function, so often a variance and whatever parameters you have to look at the correlation between different points. So if this is the model, this is like the prior setup, you'd go away and do some model runs, and that's your data D, and then you update this, you fit this to those D model runs. Okay, that's like the standard form. Okay, so you can fit this, if you're a Bayesian, you can fit it like a Bayesian, put priors on the betas and parameters, or you could fit it using maximum likelihood as well. I am a Bayesian, but I like to have an easy life, so I use something called Bayes linear fitting, which is kind of, it's something developed by Michael Goldstein, who's at Durham. And the idea behind Bayes linear fitting is that rather than putting whole distributions on things you don't know, prior distributions, you work only in means and covariances. So for everything I don't know, I give it a mean and a covariance. And I use these two equations here, which are called updating equations. Takes my prior beliefs, updates them with the data D, and gives me updated beliefs. So I put means and covariance in, and I get means and covariances out. I don't get distributions. Okay, and the advantage is that it's an awful lot quicker. Those two equations are it. You don't need to do any MCMC or anything like that. Okay, so that's how I, when I go over the two examples, that's how I fitted both of them. Okay, so that's sort of a brief introduction to emulation. Now I'll talk about two examples that I worked on in energy policy. So, as we've heard a lot this week, it's common to use these large computer models as decision support tools for government energy policy. And since 2013, the UK government's had this electricity market reform programme to look at reforming the electricity market. And the government department, which is now Bayes and used to be DEC, have a set of models that they use to investigate different policies under this programme. And so they have a bunch of models. I looked at one model in particular, which is a generation investment model, but I looked at it for two different problems. So one was quantifying uncertainty in wholesale electricity price projections, and the other was to do with what David Newbury was talking about on Monday, which is choosing the parameters of a renewable support programme called strike prices. Okay, so the first example, so this computer model was used to basically to project what wholesale electricity prices should be. And this was used in a lot of different government policy areas. It's used as the input for a lot of different models. So Bayes were interested in understanding what the uncertainty in those projections are. They normally would just publish a central scenario and a high and low. And they were interested in sort of understanding, you know, they would do this by putting in high and low scenarios as inputs, and they wanted to understand if they could put a probability distribution on these wholesale electricity prices. Okay, so I did a secondment at Bayes to investigate this, if I could put basically uncertainty bounds on these wholesale electricity price projections. And so this model that they used, it wasn't too slow, so it took an hour to do one run, basically. But there were limitations, technical limitations, such as it couldn't be batch run or anything like that. So it was quite, even though it was not too slow, it was still quite difficult to get a lot of model runs from it. Okay, so I looked at four sources of parametric uncertainty. I got these by talking to people at Bayes. Gas prices, demand, deployment of offshore wind, and the carbon price. And so I did this by emulating this model that they were using for the wholesale price projections, and I also added on a bit of structural discrepancy. I don't think I'll have time to talk about that. So I was able to do a fair few model evaluations, 150, which I had as a training set, and I did another 60 as a test set. Okay, so for this particular problem, I'm looking at the wholesale electricity price, and it's a time series. Okay, so it's a time series over the next 21 years at the time I did the study. So I didn't want to have to build a different emulator for each of the 21 years. So I used principal components analysis to break it down to the sort of the 6 main principal components, and then I built an emulator for each of the 6 components. Okay. Use this emulator here, just like I showed you before, some betas, some basis functions, and the stochastic process. And I use this Gaussian correlation function. Okay. So then I had to set prior means for my delta, my sigma squared, and a mean and covariance matrix over all of my betas. So I fitted that emulator. These are some plots to try and convince you that it fitted well. So the one on this is the first two principal components basically, and this is my test set of 60 model evaluations. So I built an emulator on 150, and then I said, how well does that emulator fit the 60 in my test set? The cross is the output of the model, and the bars are what my emulator was predicting. So it did quite a good job. Much more uncertainty for the second principal component, but the majority of the variance was in this one. Okay, so I fitted my emulator, and then I had to go away and combine this with a model for the parametric uncertainty over these 4 input parameters. These are the assumptions that I used. It's kind of just an example, so I'm not pretending that this is the actual distribution that you should use. You could use whatever you want, but I got the parameters by taking the scenarios that Bayes were using. So the central input where I've got mean 0 means that's the central Bayes scenario for each of the inputs, and the variance corresponds to a 95% interval being their high and low scenarios. Okay. And I tried to do a bit of an expert elicitation exercise to get the correlations. So I sat down and spoke with a bunch of people at Bayes and asked their opinions on correlations between the different parameters. And unfortunately, each one of them gave me a different answer. So I went with the most senior. You can change those easily. So this is just an example, is what I'm trying to say. Okay. So then use my emulator, combine this with the distribution over parametric uncertainty, and this is the output plot that I produced of the distribution over the wholesale electricity price projections. So the mean projection is the solid black line in the middle. So that is integrated over these 4 parameters: gas price, demand, carbon price, and offshore deployment. Okay, so even that middle line you couldn't get using a scenario analysis because it's integrated over all these other parameters. The dark dashed lines, that's the uncertainty in that mean projection because I've used an emulator, not the real model. And the grey lines, that's then the parametric uncertainty and the associated uncertainty on that. So that's two standard deviations. Okay, and I'm not allowed to put the y-axis on this plot, but I tested this against their high and low projections, and it was actually quite similar. So that was quite good. Okay, so that's looking at uncertainty in the wholesale prices. I also did a bit of a sensitivity analysis to try and understand, or to try and show them how different inputs were impacting on the wholesale prices. And these charts are that sensitivity analysis. They're all on the same scale. So the mean is the solid black line, and I think it's gas price in the top left, carbon price, this one's offshore wind, and this one's demand. And the dashed and dotted lines are just saying, okay, what if I use a high gas price and a low gas price, and then integrate over uncertainty in the other 3 parameters. Okay, so it just gives you an idea about what impact the different inputs are having on these wholesale prices. Okay, so that's that first example, wholesale price projections. The second example is strike prices, and as I said, David gave a good introduction to these on Monday. So as part of electricity market reform, the government held auctions to support renewable technologies. The renewable generators could bid into this auction, and they would be guaranteed this fixed strike price, most of them over a 15-year period. Okay, so originally it was the case, I think, that everyone was just going to get the same price, and the government were going to set what the price was, and then they decided to make it an auction, but they still had maximum prices. So they set what were known as the administrative strike prices, which are the maximum prices over time, so each one was a time series that they were willing to award each of the technologies. Okay, so my job was to look at these strike prices. First auction was held in late 14, results in February 2015, so I did this after that first auction. I was looking back on what had happened. Here's some newspaper articles. These are all headlines coming out of this strike price auction to try and show you that people do care about this. Okay, so the decision problem. So they had this generation investment model, and they had a bunch of scenarios for different parameters, and what they were doing at the time was they were running it for different sets of strike prices under different scenarios and saying, well, you know, if I pick these strike prices, I cover roughly these scenarios, so those are the ones I'm going to go with. We wanted to do a better job of that. They had 3 targets to meet, 3 targets up here. Wanted cost to be less than 7.6 billion. They wanted more than 30% of renewables, and they wanted emissions below 100 grams of CO2 per kilowatt hour in 2030. So what we tried to do is to use an emulator to be able to say that if they picked these strike prices, they would have, you know, X probability of meeting these 3 targets, or of meeting the targets individually. And, you know, that's difficult to make this decision under uncertainty, because the model takes an hour to run, so they were limited to just running a small number of scenarios. So the problem with this model, well, it's the same model, but it's a different problem. The problem with this question compared to the one before is that, you know, this problem was much more complicated. It had a much larger input space, and I was able to do far fewer runs. So partly that's because in the first problem I was at base for a month, and I could sit there and do as many runs as I wanted. For this one, I only had a couple of days there, so I was only able to do a very small number of runs. But actually, the number that I did for this problem was more representative of the number that they would generally do for a policy problem. Okay, so the number of runs, or the amount of data that I had to fit the model, was quite limited compared to the one I did before, where I had 150. And what I found was that when I was trying to fit the emulator to the data points, it just didn't fit very well. I fitted it to different regions of the space, and I got different answers. It seemed like the coefficients that I was fitting, they were varying in different regions of the space. And kind of a standard approach to deal with this is often to split the space up into different areas and fit a different emulator in each one. But this wasn't an option to me here, because I just didn't have enough model runs to do that. I also found that my uncertainty was underestimated in areas I didn't have much data. So when I was extrapolating away from areas where I had lots of data, I was getting the uncertainty massively wrong. And since my job is to estimate uncertainty, this is very bad, because you might argue that underestimating uncertainty is worse than not having it there at all. Okay, so I had to sort of deal with this issue. So what I did was I fitted a varying coefficient model as an emulator, and that's given by this equation up here. So it's sort of similar to the last one, that I'm modelling my output at point X by some betas times some basis functions, but now rather than just having one stochastic process, I've got one associated with every single beta. So what this is doing is it is allowing me to model the variation of my beta coefficients as I move around the input space. So it's sort of a generalization of the previous model. So the previous model would be this, but setting the uncertainty for I greater than 1 to be 0 in these stochastic processes. Okay. So this is good because it doesn't assume that my beta coefficients are constant everywhere in the space. So if I extrapolate away from areas, if I'm in an area with lots of data, I'll be able to estimate well what that beta coefficient should be. If I move away from an area where I've got lots of data, this is saying I should have more uncertainty in what that beta coefficient is. So it's sort of inflating the uncertainty when I move away from regions where I've got lots of data. Okay, so yes, so I fitted this as the emulator. Here's a plot just to show you roughly how that works. So I think that, yeah, this one is, so the solid black line is my true function that I'm trying to estimate. This is just like a toy example. And the emulator, the mean, is given by the dashed line and the variance by the dotted lines. So this would be a varying coefficient emulator. I only tested points between -1 and 1, and so the variance is inflating when I'm coming out of that region. This is the standard emulator, so it misses that the function changes because it isn't inflating the variance enough when I move away from the region where I've got data. Okay. Okay, so that's the emulator that I fitted. So for this problem, just to recap, my aim was to find good strike prices that met these 3 government targets. So I had 6 parameters, 6 decision parameters in the model which controlled these strike prices. I looked at 3 technologies, the 3 sort of biggest ones: onshore wind, offshore wind and solar power. And I had 8 input parameters which weren't decision parameters but which were uncertain. They're all listed here. And then I had these 3 outputs. So I fitted an emulator for each output. So I'm assuming that conditional on these inputs, these 3 targets are independent. And then I did a little model for structural discrepancy, which was kind of illustrative. And I used the same thing I did before to set the parametric uncertainty. I had these scenarios from Bayes giving me low, medium and high. So my mean was the central scenario. Variance covered the high and low, 2 times the standard deviation. So I covered the high and low scenarios, and again some correlations based on conversations with people at Bayes. So another thing which I should mention here is that when doing these emulation studies, it's often a good idea to do things in waves. So rather than just doing a whole bunch of model runs and then going away and fitting an emulator, it's often better to sort of do a small number of runs, fit an emulator, study where your emulator's not very good, go away and do some more runs there. So that's what I tried to do for this. I was only able to do 2 waves. For the first wave I did just a space filling design over all the model runs. For the second wave I used a sort of slightly clever approach, which was a criterion based design selection. So I fitted my emulator to my first wave, and then I went away and said, okay, where can I put points in this space to reduce the variance in my emulator as best as I can? So I had this criterion here, which it looks kind of complicated, but what it's doing is it's minimizing the variance of my emulator over a grid of points in the space, where each grid point is weighted by the probability of meeting the 3 targets. Okay, so I'm trying to just make sure my emulator's good in the region where I'm actually interested. Okay, and here's the plots showing the fit of this emulator, or the 3 different emulators. There's not too much to say here, except that if you can remember the first plot that I showed for the first example, the uncertainty is a whole lot bigger here, and that's because I've got fewer model runs and more inputs. But that's just a reflection of that I have bigger uncertainty. Okay, so I tried to compare this to what happened if you used a fixed coefficient emulator, but it's a bit difficult because I had to find places in the space to split it up. But I tried to split the space on 1 parameter, and then I said, okay, what happens if I fit a fixed coefficient emulator, to 1/2, and then test how well it fits on the other half, and then do vice versa, because that would sort of show if my coefficients are varying. And what you can see from the left-hand plot here, that the emulator is actually missing now a whole bunch of points. So that's sort of an indication that indeed there is a difference between the coefficients in different regions. Okay, so I went away, fitted the emulator, and then I wanted to calculate this probability of meeting my 3 government targets given a particular set of strike prices. So I did this by just doing a big search, basically. So I searched a whole bunch of auction parameters, and then I calculated the probability of meeting the targets, integrating over uncertainty in all of my 8 input parameters, and over the small amount of structural discrepancy that I'd added. And we sort of thought that, given the complexities of this, that policymakers might prefer to be presented with a sort of list of possibilities with the pros and cons highlighted of each, rather than being given, this is the answer, this is the one with the best joint probability. So this is the 5 with the highest joint probability of meeting the targets. These are just, you can probably ignore these are just what the parameters were for the strike prices. It's this part of the table that's most interesting. So these are the joint probabilities. but 14%, and these are the probabilities of meeting the individual targets. So this one is 30% renewables, this one is the emissions under 100 grams, and this one is the cost, so meeting the cost target. So this number is quite small, but actually in practice, when they did this auction, the prices that came out of it were so much lower than they'd actually projected that these are probably numbers are probably not really relevant in reality anymore. But you can see if they had assumed those sorts of costs, this is the sort of numbers they'd be getting, and it's clear from this that it was quite difficult to meet this emissions target. But if you can present these numbers, then policymakers can kind of say, well, okay, the top one's quite probable that I'm going to meet renewable and spend, but not emissions, and then the middle one, I trade off a bit of my cost target, but have a better chance of meeting the emissions target. Okay, so yes, so that's how you could use an emulator to try and find these strike prices. And I've got another plot which is just saying, so for my renewables target, this was the target, 0.3, and these were, I think, 20 of the top strike price options, and you can see the circle is the mean of the emulator, and then we've got uncertainty bounds, 95% uncertainty bounds. So you can see, you know, most of these have the expected value that they are going to beat this target, but there's huge uncertainty in these, especially the spend. This is £7 billion. Okay, so just to conclude, I guess the main thing is what I said at the start, which is that if we're using computer models to solve decisions in the real world, we have to have some way of linking the outputs of the computer model to the actual real world decision, and that means having an uncertainty specification around it. And if you have slow runs, emulators can be very useful for doing this, because they give you a method for modelling this functional uncertainty, which can then be combined with the various other sources of uncertainty. Tested this on 2 government policy problems. I hardly said anything about structural uncertainty or structural discrepancy, but that doesn't mean that I don't think it's important. And I have this new methodology for using a variant coefficient emulator, which is better at capturing that uncertainty when you don't have that many model evaluations. And I have some thanks and some references. And that's everything.
So here is the Pinson is the
opponent.
here, or the nemesis, I think is the word. So, yeah.
Thank you very much for a good talk, Amy. So I think it's very interesting that you took this angle. I think this is coming quite a lot in this field. Louis, the uncle, I don't think he's here this afternoon. It's too bad. He was part of a team where they've been trying to do a bit of the same, but somehow it's a bit, I'll say, from another angle. They wanted to have a surrogate for the unit commitment problem, so that they can bring that into investment problem. And you want to say, so I think there's different groups in our community that try to do this kind of emulation or have surrogate models. So it's very nice that you present that and contribute to this. One thing I would like you to discuss a bit more, because you make it sound like it's just easy, let's do it. It's the design. I mean, by principle, you cannot afford many runs, right? And so you have to be extremely smart about it, right?
Yeah.
So could you please tell us a bit more? So for instance, if I tell you can only make 50 runs, that's it, right? You may not be, I'll say, able to do these 2 waves and so on. So what's the strategy behind?
If I can't do it in waves, I haven't got a strategy, I don't think. I think if unless...
I think
the
that's
best
important.
thing to, yeah, it is
problem,
important.
Right?
Yeah, because what I've done there is I've just done a Latin hypercube sample over everything, and then I have, in the second problem, I've used waves to try and pinpoint where to go, and that's what's most often done in the community. So lots of problems I've seen have even 5 or 6 waves, where they just focus more and more on the area that they want to go to, and carefully pick the points every single time. And that's a good method because you know, each time you get a better and better estimate of your emulator, and that's helping guide where you're going. But if you can't estimate what your emulator is at each stage, then it's really hard to know where to put your points. Yeah. So I think that's a tricky one.
Can we learn from, I don't know, the pharmaceutical industry, for instance, because that's what they have to do. They need the minimum number of tests to have the strongest conclusion ever, right?
Yeah, I mean, I don't know if there's some way. I mean, one way to do it might be literally, you know, talking. I mean, we have an emulator. We have a prior emulator which we can get, and we can make those parameters as good as we can by talking to people and using expert knowledge and using very simple statistical models, and that might help us learn, you know, slightly what the shape of it is, and then we can go in with a few runs initially and then build on that. So I don't know. It's an interesting question.
I think it's an open.
I think it's really a
especially
difficult
here,
one.
you use very flexible modeling framework with your basis function. So you need to be smart.
Yeah, well, the basis functions, they can be quite tricky to choose as well. But I mean, I sort of say, well, we do a lot of regression modeling where you have to pick what inputs to put in, and it's kind of similar for this. But there is a lot of subjectivity in putting the model together.
All right.
Any other questions? Yes, Sarah.
I was just going to ask more about the basis functions. You said principal components, but are there any other sort of standard ways of choosing those?
So, from what I've seen, most people have a few more runs than me, and they will put in everything. So they'll put in all of the individual inputs, they'll put in the squared inputs, the cubed inputs, and maybe the interactions, the two-way interactions for everything, and then just start off with that, and then slowly as you iterate reduce those. I did mine a bit more subjectively, so I had my plots, and I said, kind of similar to you would do if you were choosing which inputs to put in a regression analysis, sort of went through and said, okay, if I put this one in, that makes my fit better. And so you could do a sort of search process like that.
Yeah, you had a question? Sorry. Yes.
Did you do, so for the first model you mentioned this, did you do any out-of-sample testing? Because if for the second model you said, okay, I fit it, I didn't find a good fit, and then I changed it to make it fit better, I guess you're in kind of big overfitting risk there. So I was wondering if you thought about that at all when you did it.
Yes, so that can be a big problem. The first one I was lucky enough to have a test set. The second one, the plots that I showed were leave one out. So I did do leave one out analysis, but it is really problematic because you can carefully choose your Latin hypercube sample over everything, and then if you do a leave one out analysis and try and predict a point, you've basically broken the Latin hypercube sample, and then you're trying to predict the point, and you deliberately put that point there so that you could predict in that space. So it can be difficult when you're looking at small sample sizes, I think. Yeah.
Especially since you're so interested in the uncertainty estimate, which are about a lot of money. So if you're not really sure how good you are with them.
Yeah, but I think that if you're doing a leave one out though, that should, in some sense, be the maximum possible uncertainty because you've taken out the point in the region that you're trying to predict. So if you've done a Latin hypercube sample and you take out a point and you try and predict that point, then that should be the hardest it gets in a sense because you've taken out one piece in the puzzle and you don't have any points there. Hopefully. I mean, if you try and go outside of the area in which your Latin hypercube sample covers, that's when you might get in trouble.
Yeah, so there's strong linkages obviously with surrogate optimization in engineering design, but you're not doing optimization over the surrogate to get new points. Is there anything that you could do in that space? I haven't seen anything done in planning models.
Yeah, that's really interesting because that's actually something that we're starting to look at in Edinburgh, so it links to what you were saying about Louis as well. I think it could be a really interesting field.
I think if you can create surrogates of big production cost models, that'd be great because then you can get a lot of points.
So I've had quite a few discussions with this back in Edinburgh, and the sort of sticking point we seem to be on at the moment is that, I mean, I don't do optimization, so I might say something wrong here, but you have you optimize some function, and from what I understand, there tends to be sort of restrictions on what that function can look like to use the clever optimization methods, like it has to be convex or something. No?
You can use metrics there's all kinds of methods.
And that can get a bit problematic because I don't know how you would force the emulator to make your function the right shape. But I think it's definitely an interesting problem. But
Chris, you have a comment?
Yeah, just following up on that because I've been part of these discussions as well. The bit if you're including uncertainty in the in the value of the objective function, then the worst complication of non-convexity is that it's not like you've kind of held your short the normal way. You've kind of held it lengthways along the blackboard, and your objective function is a big white band. And then you're not in business of traditional point, looking for a traditional optimal point. You've got to find the regions which could credibly be optimal, and it's. But probably we should talk offline about this.
That's when a lot of the nuclear weapons codes, engineering design codes, are PDE optimization that take 4 hours to run. So they'll throw out a bunch of those, get maybe 50 samples back, fit a surface, optimize using a GA or simulated annealing or some crazy heuristic just to get new points and kind of flesh it out that way, and then iterate.
Okay, Amy. Thank you very much. Very good talk.